Assalamualaikum. Today we are going to present about synthesis, properties and electronic applications of titanium oxide nanomaterials. So I am Muhammad Akmal Zazrin and my group members are Lamzi Shin, Syam Wei Bin, Nawal Shifa Shafi'i and Shahida Idris. So for the first part, I'm going to present about general information on nanotechnology. Nanotechnology can be defined as the skill, art or device or system that manipulates phenomena at approximately 10 to the power of -9 meter scale. And the properties of TiO2 nanomaterials can be explained in terms of specific surface area of catalyst, types of crystalline structure, surface and surface morphology, while its fundamental properties are diverse and flexible morphology. Crystallographic arrangement allows for both rutile and lattice modification, high diffraction index, strong light scattering and incident light reflection capabilities. It also have E number that is E171. Then for types of TiO2 nanomaterials, TiO2 nanomaterials can be classified into three types. There is nanotubes, nanoparticles and nanofibers. For the first one, we're gonna look at nanotubes. Nanotubes have high specific surface area and ordered nanotubes arrangement, while nanoparticles have unique optical and electrical properties and it have diameter less than 100 nanometers. For the last one, nanofibers, it have diameter of 100 nanometer or less and made up of organized nano component, while usually its bed form comes from cellulose or collagen.
My name is Shahida binti Idris. I will present about structure and properties of titanium dioxide. Titanium dioxide unique chemical, biological and physical properties because of their noble nanoscale size compared with larger particles of the same material. There are four types of mineral forms which are anatase, rutile, brochite and TiO2b. Structure of anatase, rutile, brochite are all built on the connection of slightly distorted TiO6 octahedron building blocks and also TiO2b crystal structure. Structure rutile and anatase can be described in terms of chain of TiO6 octahedron in which an octahedron of 6 oxygen ions surround each titanium ions. Under different pH conditions from acid to basic, the phase transition size of TiO2 nanoparticles are shown to be varied from 6.9 to 22.7 nanometer, accompanied by the change in morphology of the nanoparticle. Titanium dioxide is N-type semiconductor based on oxygen vacancy in the titanium lattice but with a larger bandgap. Light absorption ability also have in titanium dioxide, especially small in titanium dioxide where the direct electron transition between the band center are depressed by the crystal symmetry. It suffers from quick recombination of photoexcited charge carrier. It is restricted solely to ultraviolet light, which makes up only 5% of solar radiation due to its large bandgap. To enhance the properties of electronic structure, modification process have been introduced, which is black titanium dioxide formed by hydrogenation process. Second, long wavelength absorption, and lastly modified with copper oxide co-catalyst. Thank you.
Morning to all, I'm Choi Bin. Today I'm going to present about the synthesis of titanium oxide nanomaterials. In general, we obtain the nanomaterials from natural and engineering process. For natural, we obtain the nanomaterials from hair, milk, blood and other else, while for engineering process, we produce the nanomaterials with the desired properties. And it usually classified into liquid phase, solid phase, vapor phase and gas phase. The first method to produce the titanium oxide nanomaterials is by the solder method. This method will be start with a precursor, usually the metal alkoxide or metal chloride. The precursor will undergo hydrolysis process to form a solution. Then it will be dehydrated to form a gel. Next, it will be rapid dry to form an aerogel. The final products will be produced in thin films by spin or dip process. There's a few examples of producing the titanium oxide nanomaterials by this method. And one of the example is titanium oxide is produced by adding titanium chloride drop by drop into 50 ml of water at approximately 0 degrees Celsius. And then the chloride of titanium oxide is dialyzed until pH is between 2 and 3. And finally, the solvent is removed by rotary evaporation. These methods are able to produce high purity and uniform nanostructure titanium oxide nanomaterials at a low temperature. The second method to produce the titanium oxide nanomaterials is by the solvothermal method with polymer gel. At first, the polyvinyl alcohol PVA will be undergoes dissolution process at a temperature of 70 degrees Celsius, and then it will be cooled to room temperature. Next, the ammonium citrate titaniate will be added to the PVA, and the mixture will then dry using a microwave. And next, the mixture and the solvent medium ethanol will be placed inside a tavern reactor with a stainless steel autoclave at a temperature of 230 degrees Celsius and for a period of 18 hours. The final products will be corrected and dissolved in the water at a temperature of 50 to 70 degrees Celsius. These methods are able to produce the titanium oxide nanomaterials with the well-dispersed titanium oxide particles. The third method is the yttrium fiber laser ablation. This is the setup of the method. It consists of a laser beam, a focusing lens, a solvent, and a metal plate. At first, the titanium plate will be cleaned and sonicated to be ablated by the laser in a liquid media. The metal plate will be placed at the bottom of the glass vessel and the liquid will be filled above 1 nanometer above the plate. And then the sample will be ablated by the monomode yttrium doped fiber laser that operate in a continuous wave mode with a maximum power of 200 watts. The scanning speed will be maintained at 5 mm per second and kept in relative movement with the titanium plate. And the final product will be obtained directly in the liquid. Thank you.
Hi and Assalamualaikum everyone. I am Nur Nama Shifa binti Muhammad Shafi. I would like to present about the flame synthesis. So this is the flame synthesis. The figure 1 shows the experiment setup of the flame synthesis of the titanium oxide nanoparticle, and the figure 5 shows the schematic figure. So, step 1. The flame reactor is set up consists of precursor delivery system, particle collection units, and vacuum generating chamber. Step 2. The TTIP is set up in a bubbly unit which is placed an oil bath maintained at 125 degrees Celsius to ensure the supply of precursor to the burner and the reaction chamber. The final step will be the chemical gas with the precursor vapor is passed through to the central tube of the burner where it decomposes and produces titanium oxide nanoparticle. The next synthesis will be the chemical vapor synthesis. This kind of chemical vapor synthesis has many more synthesis, but in this presentation we would like to present you about the using flash evaporation as precursor delivery method. So this is how it works. I mean, like, this is the figure of the synthesis. The step 1 will be the titanium diisopropyl by tetramethyl heptane diunate will be synthesized into titanium oxide nanoparticle. The solid precursor is continuously and manually fed into the flash evaporator and evaporated with carbon dioxide laser with apparatus 95 watt. The step 2 is after the precursor is evaporated, its vapor will be carried by the helium steam into the hot wall reactor. The titanium oxide nanoparticles are formed by the reaction of the vapor and oxygen at temperature 1273 Kelvin and a pressure of 20 mbar. The final step will be particles are collected in the thermoperiodic particle collector. Method can be used to produce high purity and high density nanomaterial with high production rate. And then we will proceed to the electronic application. The first application would be the photocatalysis.
So this is how it works, and this is the figure of the photocatalysis. So what is uses? First, degradation of pollutants. Second, photodiamid and third, reduction of carbon dioxide, and fourth, water splitting. So the next application would be solar cell. So this is the 5 types of solar cell, which is the SST, polymer inorganic hybrid solar cells, quantum dot synthesis of solar cell, inorganic solid state solar cells, and the last one will be perovskite sensitized solar cells. So this is how it works, and the figure shows the inside of the application. So this is how it works. So that's all for me. Thank you.
Okay, my name is Lamzi and I'll be extending upon the applications I've expounded by my previous team members. Now, my first application are lithium-ion batteries. Now, lithium-ion batteries offer high energy density. It is flexible, as a lightweight design, and it has a very long lifespan. Now, TiO2 is considered a promising lithium-ion battery anode because it is stable over multiple cycles. It has safer lithiation potential relative to graphite. It has a reasonable capacity. It has a high rate capability. It is non-toxic. It is low cost and has a working potential greater than 5 that can highly limit the reduction of electrolytes or the formation of solid electrolyte interface layer. Now, sensors. There are 3 kinds of sensors, in which there are gas sensors, there are biosensors, and there are chemical oxygen demand sensors. Now, this is a diagram illustrating the processes involved in the various sensors that I've already stated above. And next, we have memristors. Now, what is a memristor? A memristor is a non-linear, passive, and two-terminal device that maintains a functional relationship between time integral of voltage and current. Now, the oxygen vacancies in oxygen deficiency migration is due to the applied voltage, which causes these changes in the device's resistance, which is shown as the diagram that I pasted into the slide. Now, the future scope. What can TiO2 nanomaterials be used in our future? Now, there's research in medical science in which photocatalytic property of titanium dioxide can be used in order to trigger drug release. Now, in the conventional sense, if we were to take a pill and we were to swallow it, we have to wait for the outer shell to dissolve, and only then the drug will be released in our system, whether we want them to release it at that point or not. Now, but using TiO2 nanomaterials, we can prevent the premature drug release by using ultraviolet light as a release mechanism, and this allows for more circulation time in the case of cancer treatment to effectively target cancer cells. Now, photocatalytic applications can be improved upon. Now, there's research in exploring efficient photocatalysts. There's one research involving the photocatalytic composition of methyl orange over sterilite modified TiO2 photocatalyst, and this provides promising strategies to explore highly efficient photocatalysts, and at the same time achieve the objective of promoting further applications of TiO2 nanomaterials in the environmental fields. Next, we have nanomaterials and carbon composites, and these synthesized over 2 loading cycles will exhibit a higher photocatalytic activity. And next, we have the conservation of nature. Carbon nanotube supported TiO2 nanomaterials exhibit high photocatalytic activity and stability. Now, this shows great potential in the treatment of wastewater, and in the case of long TiO2 nanotubes and graphite oxide hydrogel absorbents, it can be used as absorbent to absorb the antibiotic pollutants that have somehow escaped into our aquatic systems. And what are the challenges involving TiO2 materials? One of it involving the potential health challenges involving handling TiO2 nanomaterials. Now, there are potential exposure routes of TiO2 nanomaterials via the respiratory system, through our skin absorption, and through our digestive systems. Now, there are previous cases in which 2 females working in printing plants who have died due to this respiratory failure. Now, this may be due to long exposure to TiO2 nanomaterials, but without any solid research backing up this thesis, we can't say for sure, because there's a lack of systematic knowledge of toxicology, epidemiology, and a lack of testable sample size from the workplace exposure of nanomaterials. And there's also environmental exposure, in which there is risk of intentionally or unintentionally introducing these nanomaterials into our environment. Now, for example, if we were to shower and the shampoo in our hair has a small degree of TiO2 nanomaterials embedded in it, and this may get washed down the drain, and eventually it would end up in our aquatic systems, and it would possibly influence our embryonic development stages of any biological creatures that it comes in contact with. And then once again, there's very little known about the special characteristics of nanomaterials due to the lack of obligation or responsibility by corporate entities in the form of any sort of standardized methods produced. For example, the OECD guidelines. Now, how do we fix this? Now, there's a research by the name of Veronica Adam and her various constituents that underlines the need to take into account of nanospecific properties such as crystallinity, size, aggregate state, surface area, and particle number. Now, we hope to adapt ecotoxicological studies to NP-specific properties via new methods of measurement and new metrics for ecotoxicity thresholds. Now, what can we conclude from our research, from our study into these nanomaterials? Now, TiO2 nanomaterials can be classified into three subtypes, which are nanotubes, nanofibers, and nanoparticles. The properties can be explained in the terms of specific surface area of the catalyst, the type of crystalline structure, and the surface morphology. Now, the synthesis can be divided into either liquid phase synthesis, gas phase synthesis, vapor synthesis, and solid phase synthesis. Electronic applications include photocatalysis, solar cells, lithium-ion batteries, sensors, and membristors. The future of TiO2 lies in medical science as a drug release mechanism and for various environmental applications. And with that, I'd like to thank our lecturer for viewing our presentation, and I'll bid you a good day.